The question is, could you do an example on the calculation of stress and deformation for a cylindrical shaft subjected to torsion? In this example, I will consider a segmented shaft. This is the problem that I have chosen here. We have a cylindrical shaft with a solid cross-section that has three segments, AB, BC, and CD, each with different radius and length. The shaft is fixed at point A and subjected to concentrated torques at points B, C, and D. The shaft is made of the same material throughout, which has a shear modulus of 80 gigapascal. These are the questions. Determine the maximum shear stress in the shaft and determine the angle of twist of the shaft at points B, C, and D. Just to refresh our knowledge on the pertinent equations here, this is the summary slide that I had in the theory video. We know the shear strain varies linearly with the radius rho starting from 0 at the center. The shear stress does the same. The stress produced by the torque, the shear stress produced by the torque is marked on this differential element, which is taken at a point like this. So the only non-zero stress component induced by a torque like this is the shear stress, and more specifically, this is tau x theta, shear stress on the x-plane in the theta direction. Here is the torsion formula for calculating the shear stress at a given radius rho. Tau equal T rho over J, where J is the polar moment of inertia given by this expression. The polar moment of inertia for standard sections can be found in many different sources, including books. For a solid circular section, it's pi r to the power of 4 over 2. We calculate the shear strain simply by dividing the shear stress by the shear modulus. When we have a shaft with a constant torque, constant radius and therefore constant polar moment of inertia, and a constant shear modulus, this is the equation for calculating the angle of twist. X here is the length of the shaft. In other words, if you take a shaft, fix it at one point and apply a torque at the other end is going to twist by this angle. And the units would be radians. When the shaft is segmented, like in the problem we have, these equations are still valid within each segment. So let's see how we apply these equations to our problem. The first step in analyzing a segmented shaft like ours is to determine if the shaft is statically determinate or indeterminate. So how do we do this? Well, first we cut the shaft out of the support or support and complete the free body diagram for it by marking the unknown support reactions on it. So in our case, we only have one support at point A. So this is the torque at that support, TA. Then we count the number of unknown support reactions, and obviously in our case, Nu, the number of unknown, is 1. Then we see what kind of meaningful equilibrium equation that can be written down for the free body diagram of the shaft. In our case, it will be a torque equation like shown over here. So we can write down one equilibrium equation, and therefore Ne is 1. So since Nu and Ne are equal to each other, what we have is a statically determinate problem. So the method discussed from this point on applies to a statically determinate problem. While many of the steps are the same for both types, a different method involving a displacement compatibility condition is needed for the statically indeterminate problem. Returning to our problem, which is a statically determinate problem, step number 2 is to determine the internal torques on each of the three segments. First, we need a sign convention. Our sign convention here would be counterclockwise torque with respect to this x-axis is positive. So for example, this is a positive direction for the torque. You can use the right hand rule to figure this out. What you do is you hold your thumb in the direction of the positive x-axis. Then the direction of your fingers will tell you the positive direction for the torque. So how do we find the internal torques? Well, we section the shaft at a point inside the segment of interest, separate the shaft into two parts, choose one side to analyze, complete the free body diagram for that side, and then write down an equilibrium equation like this in order to solve the internal torque. So let's consider at least one of those here. So these are the details for sectioning in the segment AB. So here's the right side, here's the left side. So I'm marking this torque TAB in accordance with the sign convention. So that will be the positive direction for TAB. And of course on the other side, TAB is going to be acting in the opposite direction. Magnitude is the same, directions are opposite. So it's convenient to analyze this right side, because if I were to analyze the left side, first I need to find the support reaction, which you can do, but this is a little easier to analyze. So here is my equilibrium equation for the torque. I'm summing up the torque in the counterclockwise direction. TAB goes in the clockwise direction, so that goes in as a negative term. 15 kilonewton meter acting at point B goes in the counterclockwise direction, so that goes in as a positive number. 8 kilonewton goes in the clockwise direction, so we have a negative sign in front of that. 2 kilonewton meter goes in as a positive term because that's a counterclockwise direction. So now simplifying this, we get TAB of 9 kilonewton meter. Here are the details for sectioning in BC, and here are the details for sectioning in CD. So here's the summary of what we got. TAB is 9 kilonewton meter, TBC is minus 6 kilonewton meters, TCD is 2 kilonewton meter. We know the torque is constant within each segment, right? It varies from segment to segment like this, but within each segment it is a constant. Step number 3 is to calculate the stress within each segment and find the maximum for the shaft. So here's our problem. Here are the values of the internal torques that we got in the earlier slide. And here are a couple of things from a theory slide that's going to help us. First, we recall that on a given cross-section, the shear stress due to the torque vary linearly starting from 0, right? So the maximum shear stress on a given cross-section is happening at the outer fiber of the shaft. We can calculate its value using this torsion formula, which says tau equal T rho over J, where T is the torque, rho is the radius, J is the polar moment of inertia, which is given by this equation for a solid circle, right? Half times pi times r to the power of 4. So the two key takeaways are that on a given cross-section, tau max is given by this equation, where T and J pertain to that particular cross-section. R is the radius of the section, and tau varies from segment to segment since T, R, and J vary from segment to segment. So here's a summary of everything that pertains to the stress calculations. First, I calculated the polar moment of inertia for the 3 cross-sections. For example, the polar moment of inertia of the segment AB is half times pi times RAB to the power of 4, where R is the radius of the circle representing the cross-section in the segment AB, which is 30 millimeters. So I represented that in meters so that my polar moment of inertia will be in meter to the power of 4. I get this value, 1.272 times 10 to the minus 6 meter to the power of 4. You can follow these calculations very easily. Then I use the torsion formula to calculate the maximum shear stress in each of the 3 segments. The torsion formula is TR over J, and here are the values of the torques, and here are the values of the radius for each of the 3 segments, and now we just calculated the values for the polar moment of inertia for each of the 3 segments. You substitute these numbers in a unit-wise consistent manner in order to calculate the maximum shear stress. For example, the shear stress in segment AB is calculated to be 0.2123 times 10 to the 6 kilopascal. So now, since this is a big number, we have a big factor here, I'm representing this in megapascal. So that will be 212.3 megapascal. Following similar procedure, I get a value of 30.4 30.5 megapascal for the shear stress in segment BC, and 159.4 megapascal for the shear stress in CD. So looking at these three values, it is clear this is the maximum of the three, right? And therefore the maximum shear stress in the shaft is 212.3 megapascal, and it happens to occur in segment AB. And this picture from the theory slide tells you exactly what is it that we just calculated, right? We calculated this shear stress component, the shear stress on the x-plane in the theta direction. That's what these are. X-plane is the plane perpendicular to the x-axis. That'll be this cross-section right there. Step number 4, calculate the values of the angle of twist. From the theory slide, we know that if I have a simple shaft with a single segment, right, of length L, this is the formula for calculating the angle of twist. In other words, if one end of that simple shaft is fixed, the other end is going to twist by this angle. But in our problem, we have 3 segments, but I can still calculate the angle of twist for each segment using this formula. For example, angle of twist of point D with respect to point C can be calculated using this formula. And similarly, angle of twist of point C with respect to point B can be calculated using this formula applied to segment BC and so on. But the absolute angle of twist of point D is going to come from not only the angle of twist of this segment, but also the angle of twist of this segment and this segment, right? So they need to be algebraically summed up in order to find the net angle of twist of point D. So that's the approach here. So let's first go ahead and calculate the angle of twist of each segment. So it's understood that if one of the ends of that particular segment is fixed, the other end is going to be twisting by this value that we're going to calculate right now. There are 4 parameters in this equation: torque T, length L, the shear modulus G, and the polar moment of inertia J. It's convenient to have values of all 4 parameters in the same place, so I collected the values and listed them in this table right here. So here are my calculations for the angle of twist of each segment. Let's go over one of them. Phi AB is TL over GJ evaluated for segment AB. T, the torque, is 9 kilonewton meter from this table. And then length is 1 meter. G is 80 gigapascal. We're going to convert that into kilonewton per meter squared to be consistent. So I'm multiplying that by 10 to the 6. J is 1.272 times 10 to the minus 6 meter to the power of 4. And you simplify that, you get 0.088 with no units. All of the units will cancel out to give you no units, and that's the way it's supposed to be. Angle is supposed to be calculated in radians. Now we can of course convert that into degrees by multiplying this by 180 and dividing that by pi. So in this particular case, I get a value of 5.07 degrees for phi AB. Now you can follow these 2 steps very easily. So here I get a value of minus 0.525 degrees, and here for segment CD I get a value of 10.28 degrees. Here are my calculations for the angle of twist of each of the 3 points B, C, and D. The angle of twist of point B with respect to point A comes only from the angle of twist of the segment AB, which is 5.07 degrees. The angle of twist of point C comes from both the segment AB and the segment BC. So you add the 2, we get a value of 4.55 degrees. The signs are automatically taken care of because we are following a sign convention, right? Remember, the counterclockwise torque with respect to the x-axis was taken to be the positive direction for the torque, right? So that takes care of the sign for the angular twist as well. Now to find the twist of point D, you add the 3 values. So you get a value of 14.83 degrees for that.